We present SparseCam4D, a novel framework for spatio-temporally consistent 4D reconstruction from sparse cameras, and performs high-fidelity novel view synthesis results than previous methods. 4D Gaussian splatting has achieved impressive results for dynamic scene reconstruction. It represents the scene as a set of 3D Gaussians in spacetime, deformed through a hex-plane structure and a small MLP to produce temporally consistent renderings. However, 4DGS and all existing multi-view 4D methods rely on dense synchronized camera arrays to provide sufficient geometric coverage. Such costly lab setups severely hinder broader adoption and scalability. When we drop down to just 3 cameras, the reconstruction quality collapses dramatically, as shown on the right. This raises a practical question. Can we achieve high-fidelity 4D reconstruction with only 2 or 3 cameras? A natural idea is to use a video diffusion model to generate auxiliary views from the sparse input cameras, enriching the observations before feeding them into 4DGS. However, this introduces a fundamental new problem. The generated frames suffer from 2 forms of spatio-temporal inconsistency. First, temporal inconsistency. Frames generated for the same viewpoint at different time steps flicker and are geometrically unstable across time. Second, spatial inconsistency. Frames generated for different viewpoints at the same time step show mismatched object positions and appearances. If we feed these inconsistent generated frames directly into 4DGS optimization, the distortions get baked into the scene geometry, leading to severe blur and reconstruction failure. To address this, we propose SparseCam4D, built around the key insight that these spatio-temporal inconsistencies are not random noise. They are structured distortions that can be explicitly modeled. Our core contribution is the spatio-temporal distortion field, or STDF. STDF is a K-planes factorized field operating in a 5D coordinate space of position x, y, z, time t, and pose index s. It uses 9 two-dimensional feature planes, covering all pairwise combinations except the TS plane, to encode how generated frames deviate from the true canonical scene. For each generated frame at time t and pose s, the 5D position of every Gaussian is projected onto these planes. The features are aggregated and decoded by a lightweight multi-head MLP, producing per-Gaussian distortion offsets in position, rotation, and scale. During training, real camera frames supervise the canonical 4D Gaussians directly with photometric loss, while generated frames supervise distorted Gaussians with a perceptual loss. This decoupling prevents generated artifacts from corrupting the underlying scene geometry. Critically, once training is complete, the entire STDF is discarded. Only the clean canonical 4D Gaussians are kept for inference. This means our method adds 0 overhead at test time. The distortion field is purely a training time auxiliary mechanism. Our method achieves state-of-the-art rendering quality in comparison with other methods. With only 2 to 3 input cameras, our method achieves high-quality novel view synthesis with sharp details, stable dynamic regions, and minimal artifacts across diverse scenes and viewpoints. In comparison with multi-view 4DGS methods, our method maintains consistently higher rendering quality, while these methods degrade severely due to the lack of dense camera coverage. Compare with sparse view 4DGS methods, our approach achieves significantly sharper geometry, cleaner appearances, and fewer artifacts across all scenes. Thank you for watching.